Hey everybody, so welcome to the talk. So this is basically a story about how Coinbase responded from a specifically MongoDB slant to all of the crazy enthusiasm we experienced over the course of 2017. So, and I want to preface this by saying that we were a team of non-MongoDB experts getting plunged into this situation originally. So you get to watch kind of how we changed our tactics. And you might see a little bit, if you've gone through a similar experience, you might see some parallels. Quick intros. I'm Luke. That's Michael, Jordan. And we're on separate teams, but I want to be very clear. We're just three of the people who are involved in this crazy year. Pretty much the entire company was full-time involved, way more than full-time involved, including absolutely the entire engineering team. So just a quick intro for those of you who don't know Coinbase. We consider ourselves to be the easiest and most trusted way to buy and sell digital currency. So that's everything from Bitcoin to Ethereum and Litecoin, as you see on the graphic. And this is really what we were. And this is what a lot of people think of us as. But over the past year, we've really grown into a lot more. We've added a lot of additional products, and we're now beginning to try to branch out into this idea of the utility phase of crypto. So if you're familiar with most of your friends who own crypto, or if you own crypto, most people are initially in the game to make money, and we call that the invest phase. But what we're currently branching out into is this idea of the utility phase. Like, how can we actually make these useful to people in real life? So that's what we're doing in the future. Quick intro to our stack. We are entirely on AWS. We heavily leverage MongoDB for Coinbase and several of our other products. We are a Rails shop, so is our primary web framework. And Rails interfaces MongoDB a lot. When you think about what do we explicitly use MongoDB for, pretty much everything. So your identity, all the information about your payments, or your transfers, transactions, what devices you use, the addresses you're sending it to. We have over 500 different MongoDB collections, and as such, that many Rails models. So taking a step back, and when you think about Coinbase, actually the most important number here, well, these are both important numbers, but we store $20 billion of user assets. And when you think of a digital asset, really all that is tokens or some currency associated with a private key. If that private key is leaked in a log file or something like that, those assets could be stolen immediately and irrecoverable. So security is one of the most important elements of what we do at Coinbase. And we have 20 million customers who we need to protect to be able to uphold that reputation as the most trusted. So up until sometime in 2017, our number one strategic priority, everything we talked about as an engineering team, was do not get hacked. And it made a lot of sense, right? But this is really a presentation about how that priority changed a little bit and how we've begun to think about Coinbase as a company that views don't get hacked as an equal priority along with build reliable systems. So let's give you a little bit of context here on what our traffic looked like. So this is, actually the end of this is around this time last year. So we're seeing, in my opinion, barely any traffic. This is uncached requests per minute to our backend core API service. And we were trickling around 15,000 RPM. And really, we just weren't really worried about performance too much. I mean, it worked fine. And if we were to have picked a line where we might have started to get worried, we would have drawn this red line here at 100,000. Actually, we did draw that red line. And this red line was on all of our homegrown dashboards. It's like, well, if it ever gets there, it's time to start doing some work. But in May and June of 2017, basically the price of Ethereum specifically shot up. And as a result, interest in cryptocurrency exploded. And as a result, traffic to our website exploded. Now this is for May and June of last year. And you can see these are averaged over 4-hour buckets. So there were entire days where we were consistently over that 100,000 requests per minute line. And the best way for me to probably visualize the way that our site handled that load is with this explosion thing. We were not up. We were not doing very good. We were making the news for all of the wrong reasons. I remember being in a room, we're all in a room just like on our laptops trying to figure out what to do. And the New York Times just published an article like, major cryptocurrency exchange Coinbase down for extended period of time. And it was like, man, like, how did this happen? So to be clear, Mongo was what was blowing up. And we were confused. And we were in the midst of all this firefighting, and we're like, what do we do? So found this great graphic that kind of described how we thought about it at the time, which is like, what are our low-hanging fruit? What are the fruit we can just pick up off the ground, right? And for us, at that point in time, we didn't have some of the advanced monitoring we're going to talk about later, and we were just thinking about this in terms of vertical scale, like how can we make each of our clusters bigger? How can we split apart our different collections, right? Because joins aren't forcing us to keep those together. How can we upgrade off of our old versions? How can we make sure that we're on the latest, like Wired Tiger, where we get document level locking? And those are low-hanging fruit. And so leading up, this is the original chart I showed you. This is our effort as part of a project to upgrade MongoDB. And you can see that the orange little lines there are when we made an upgrade, and the blue are where we tried to split them apart to gain a little more room for vertical scale. And we weren't making much progress. I made this little chart here about, these are like 5 of our most important clusters at the time. And if this were an MTA, like subway map thing, like we weren't getting very far very fast. You wouldn't want to ride that, right? So over the course of all of these explosions, we realized that Wired Tiger, in our mind, Wired Tiger was the way out because we were seeing all these weird locking issues. I mean, if any of you know, the query playing on 2.6 was horrendous, sorry. And we were just running into all these weird issues. So in order to get ourselves out of this mess, we just went into full cowboy mode, and we would find ourselves down, and we would begin doing upgrades. So this is that same chart here, where you can see how when we began to see that major spike in load, we would do things like splitting out clusters. Like every other day, we'd take a little downtime window, we'd split apart some clusters, we'd upgrade, we got to 3.0, we got to Wired Tiger, and every day, every time we did this, we were actually able to get to a higher level of traffic. And it was really exciting. We're like, oh, wow, this is the way forward. Like, wow, aren't we so smart? And really, the issue, we got everything. And here's like a fun way of visualizing it, right? We split things apart. We added analytics nodes to some of our clusters so we could take reads off of our primaries. And we thought we were doing pretty good, but we're beginning to see issues that we just didn't understand. And we were seeing, we'd see frequent spikes in traffic where we would basically go down, but we'd already made all these upgrades that we thought would get us out of the problem. So, yeah, Michael's going to talk a little bit about how we got out of that.
Yeah, so is this working? Yep. As Luke said, we had this imaginary red line that was around 100,000 RPM. And every time we hit that sort of spike, we would blow up, and we just had no visibility into what was going on. So as an example, this is how we sort of looked in normal traffic mode, this nice little icing layer of MongoDB on top of what is mostly Ruby time. And latency is around 50 milliseconds per request. When we blew up, we saw something like this. This 100 times spike in latencies across requests, and this really interesting pattern of half Ruby, half Mongo time. And we affectionately called this the ghost. We just had no idea what was this ghost in the system, and we kept talking about this ghost at Coinbase. So more on that ghost later. But yeah, we had no visibility into what was going on, and so we embarked on this question of where are these queries coming from, and what do these queries look like? And so we sort of spun up a project to find the answers to those questions. So the first thing we did was, we used the $comment field, and along with every single query, we would pass the source line of code and the unique request ID. And that meant what we did was we used the slow query thresholding in MongoDB and set it to an appropriate level such that slow queries would come out in our MongoDB logs. And alongside that, we would get the source line of code that the query was coming from and the request that made that query. And that was starting to provide some really useful data. However, it was not ideal because we had to take in these large MongoDB logs, parse them into something. We had no tooling on that. We weren't able to build visualizations on that sort of thing. So we went a step further, and we started logging every single query, both reads and writes, to Elasticsearch. And along with that, we parsed request size, response size, query time, the collection the query was happening on, the command, that sort of thing. And also this query shape, which I'll also talk about later. So we were logging this massive amount of data into Elasticsearch. And that allowed us to build, finally we had some dashboards and some metrics into like where things were going wrong and where these queries were coming from. So this is a dashboard we built in Kibana. The top there is the request times across the web application. Green means good. This red section is kind of what it looks like when we blew up, per se. And then on the bottom here is query time per cluster. And so different colors there represent different clusters. So this logging was probably the single biggest impact change we made in the last year. We finally had the ability to dive into some of these problems. And now I'm going to talk about some of the problems we found and how we solved them. So yeah, the first thing we saw was these outliers in response sizes. These are single document queries, and you'll see there's this one line that's hovering around the 16 megabyte mark. 16 megabytes is MongoDB's maximum document size, so this seemed like a ticking time bomb. You know, we're heading up really close to that. We've got to find out where this is coming from. And because we had added this source line of code, we could easily just mouse over one of these lines, and it would tell us exactly where that query was coming from. And you'll notice this one here is coming from this device document, find or create a device. So what was actually going on here? This is how we model our devices and user relationship. It's a many-to-many relationship. Users can have many devices. Devices can have many users. And it was kind of designed to be like this, you know, not too many edges between these nodes. But what we found when we dove into the data was it was more like this. We had these hot devices that had hundreds of thousands of users associated with them. And every time a user on that device would make a query or a write, we would pull down that massive 16 megabyte document. And you know, that was slowing down our devices cluster abysmally, I guess. And the reason for this was we had there was a flaw in our fingerprinting algorithm that caused all devices on iOS Chrome to be bucketed into the same fingerprint. And so these three are sort of like Chrome versions on iOS. And so there was a really simple solution to this, and that was to remodel this many-to-many to a one-to-many. So devices would have one user. And this was really obvious, but before we had metrics into this, we had no idea where this was coming from. So the important thing here is the metrics gave us this win, I guess. And you'll see here, you know, the response sizes just drop off here, and this is the network I/O of that particular cluster we were on. And a sort of subtle thing, in a relational database, you would normally model a many-to-many with a join table. We were heavily using the ORM, Mongoid, which is provided by MongoDB. And the way it does many-to-many relationships is it stores an array of user IDs on the device. And so as that relationship grows, your document sizes get a lot bigger as well. So we'd found one issue. We'd raised that red line to 200,000 RPM, but we were still blowing up. Ethereum was going through the roof. Bitcoin was going crazy as well. So we had to dive back in and find the next thing that our metrics showed up. And we started seeing just raw query throughput on certain clusters was really high. So we started to look at these outliers here, one of which was this applications cluster. The interesting thing about the applications cluster is it's actually a 16 megabyte collection, 17,000 documents, very small. And we were actually hosting this on a 488 gigabyte node. So you'll see, for comparison, there's the collection size, and that's how much RAM it was being stored in, right? There's clearly something wrong here, massively over-provisioned. So the solution we sort of turned to was caching. So this is Coinbase's architecture diagram. Actually, it's very simplified. And you'll see, we're hitting Mongo directly. We also heavily use Memcache for application-level caching. And so what we did was we built a Memcache query caching layer into the ORM, such that every time we made a query for a single document, we would first check Memcache to see if it was cached. And then if it wasn't, we would hit Mongo. And similarly, on writes, we monkey patched the MongoDB driver such that it would detect any writes to those queries and invalidate that cache. And because we built that in the ORM, we rolled that out across multiple clusters. We were able to reduce query throughput across multiple clusters in a massive fashion. Seen here, this is query time across multiple clusters, and we reduced some of the queries by about 90%. So we'd raise this red line again. Now we're at 400,000. We're still blowing up. There's still things we need to fix. So I spoke about this query caching that we used. One thing we probably could have explored more is sharding instead of the caching strategy. The reason we didn't do it at the time was we were under the pump. We had to get something out. We had to get the site back up, so we built this sort of query caching thing. Sharding takes a little bit longer because you have to worry about balancing your cluster. You have to worry that your queries are shaped correctly so that we're passing the shard key. But we did end up exploring sharding as well. And the way we did that was we took a very data-driven approach to that. So I mentioned the query shape earlier. Along with every query, we were passing this shape, which was a JSON string, to Elasticsearch. And you'll see here the first two are queries on events, and they pass the user ID, which is the shard key. And the last one, the user ID is missing. And so with this information, we were able to build visualizations. So seen here on the top is progress towards sharding, I guess. So these are pie charts that are split up by different routes, and they represent the percentage of queries that are passing the shard key. And then this bottom table here is a list of queries that are missing the shard key. And so our process was to go through this table and clean it up such that we were confident that the queries we were making were passing the shard key. And once we had got to this sort of nice 100% or almost 100%, we then could confidently go down the route of sharding. So as I've shown, this monitoring has really increased our visibility into things and made us able to fix things that we weren't able to see before. There's a number of other fixes that we've done that I'm not mentioning, but we're able to sort of support. This is our December and January traffic, 1.2 million, and we're no longer blowing up. And also, this is a real screenshot. We were #1 in the App Store, so both Ethereum and Bitcoin were going crazy, and this was happening as well. And if you compare that to the previous spike of 100K, it pales in comparison. So all these fixes made us strong. Jordan.
All right, so that takes us through the past and the present of MongoDB at Coinbase. You heard about how we weathered these big storms of user interest through May and June of 2017, worked through a series of fixes to raise our red line continually, and finally we made it through this huge influx of traffic when we hit #1 in the App Store. And that was great. We were really happy with how that turned out. But now that we're in this more stable period, things aren't blowing up all the time, we're realizing that we want to maintain this great workflow we had while we were firefighting. The thing about firefighting is that it's very stressful, and I'm sure you can all relate to this, where it's not something you want to be doing all the time. But the great thing about it is that it's very quick to figure out what your next best move is, because you want to obviously get the site back up as soon as possible, and it's clear the thing you need to fix next. And so you have this rapid improvement process of building the tooling you need to get there and then executing on that. So what we want now in this current phase is to be able to get these insights without waiting for this next crazy event. We want to be able to turn on this crypto mania artificially on demand, to continue building these tools to prepare for our next crazy traffic event. And another thing that's happening alongside all this is that Coinbase as a team and as a code base is growing really fast, and we need these tools to scale along with the number of engineers that are working on them. So we need them to be automated and repeatable. So of course, one way to go about doing this sort of thing is load testing tools. And load testing is one way of figuring out what your next failure is going to look like and under how much load it might occur. So generally speaking, you could break down load testing approaches into two categories. You have on one hand the approach of generating traffic synthetically by writing and maintaining scripts that are meant to emulate application traffic against your backend. And on the other hand, you can capture this actual traffic in production and then play it back against either clones of your backend infrastructure or in production in certain cases. So there are some trade-offs involved. You can come up with really great solutions using both of these techniques. With synthetic traffic, you have a lot of control over the load. But as I mentioned, you have a burden of writing and maintaining these scripts. So you add some engineering overhead to the process. And on the other hand, if you're going to capture production traffic and use it to play back later, the trade-off you're making there is that your insights are retroactive. You can only play back traffic that's the result of user activity that's already happened. But then you also don't have to be unsure that the traffic you're generating perfectly matches production traffic, because of course it is production traffic. So we thought about this, and we decided to first pursue a capture playback strategy to come up with a load testing solution that we could use to load test our MongoDB deployment in isolation. So of course, the first thing we did was sat down with a bunch of engineers, and we came up with this really awesome design that would have us recording sampled queries in Redis and then spinning up lots of instances to play those back. And it was coming along really nicely, but then luckily we decided to pause for a moment and Google it. And lo and behold, there's this first result called Mongo Replay, which, if you're not familiar, it turns out to be this great existing tool written and maintained by MongoDB, which does exactly that. It captures MongoDB wire protocol traffic on the network interface, and it saves that into a file along with some useful metadata that include timestamps and host information, and then it lets you play back that data directly to a MongoDB deployment later. So this sounded really cool, and we pursued building out a load testing tool around this, and I'll talk about that in a little more detail now. So our solution is broken into two pieces. One piece does the capturing, which I'll describe first. So we call this Mongo Replay Capture, and it wraps this Mongo Replay binary in a little sidecar container that runs alongside all of our app nodes in production. And there's a one-to-one relationship. Each app node has a Mongo Replay Capture container. So we can perform simultaneous capture of all our Mongo traffic across our infrastructure. And those captures end up getting sent to S3, where the other side of the equation, Mongo Replay Canon, which you can think of as sort of the command and control service for Mongo Replay Capture. It's able to consume those recorded captures and then kick off playbacks against MongoDB. So in a little bit more detail, Mongo Replay Capture, it's a long-running process that's always watching an SQS queue. And when it sees a job come in on the queue, it spins up Mongo Replay, and it either waits until its configured time amount is exhausted or its disk space allotment is exhausted. And then it encrypts those captures and sends them up to S3. And they also are gzipped. That's a built-in feature of Mongo Replay Capture itself. There was a problem that we ran into early on while thinking about this, which is that Mongo Replay itself can't natively capture encrypted traffic. I should have written TLS there instead of SSL, but that's OK. And this is because it's listening on a network interface, and it can't and shouldn't have access to the keys to the cert. So we ended up solving this. Actually, I should take a minute to explain that, of course, as a very security-focused company, it would be totally unacceptable to break this requirement of having all traffic between boxes in our infrastructure be encrypted. So in order to solve this, we ended up creating an extra socket on the loopback interface that our Mongo driver creates, and it writes the traffic to the loopback interface in an unencrypted way that never leaves the box, so that Mongo Replay Capture can listen. And basically, that traffic is just immediately read off the socket, and it disappears. It never travels over the network. So in that way, we can use Mongo Replay in its default form to create these captures. So going to the other side, Mongo Replay Canon. This is, as I said, like the command and control interface for all the Mongo Replay captures. It offers an admin interface that we can use to kick off and inspect and manage these captures. And shown here is the first thing you'll see when you open it up in order to create a new capture. And it's as simple as defining how many nodes you want the capture to occur on across the network, and how many duration and integer value in seconds, how long you want this capture to go for. Once the capture goes, once the time passes, it will show up as a single entry here in the manage page, where you can then see some more detail about that capture, or delete it, or go to the next stage. So another challenge, I only realized after I drew this how much it looked like rolls of toilet paper, but now that you can't unsee that analogy, please pretend that each of these rolls is representative of like a single capture that's occurred across the network. And in order to make use of these for playback, we wanted to be able to merge these into a single capture. So imagine you've got many dozens of large capture files that have occurred over many instances. We needed to come up with a way to merge these, and then also apply some selective filtering so that our playbacks could only target specific collections that we wanted to load test, or certain query shapes. If we wanted to load test in production, for example, we could filter out so that the playback had only non-destructive actions, things like that. So we solved that by creating a series of small buffers on each of these files on the one Mongo Replay Canon instance. And then a priority queue pulls each of these buffers through this filtering stage using sort of a best effort sorting algorithm based on the scene timestamps of each of these capture files. And what you end up with is a single large monolithic capture file at the end, which then you can use to play back later. And when it comes time to play back, there's another form for that. You basically set up with a target host. You have a little more filtering control has been added since the screenshot was taken. But then you can use these speed and repeat options to take a playback that was recorded at a low level of traffic and 10 exit or 50 exit or 100 exit to get the actual load test, which is the goal of this, to see how your application actually responds to whatever level of load that you're trying to test. And then you can set up some repeats so that if you've captured a short amount, you can sort of simulate what would be a longer capture. And we're planning to add some other cool things to this later on, like the ability to ramp up playback speeds over time and add some more fancy load testing stuff here. So we're just at the beginning phase right now of applying this and gathering insights, and we're really excited about how this is going to inform our performance work over the coming weeks and months. But I want to just share a little anecdote about something we found as we were building it, which is one of the things that you can do with Mongo Replay Canon is just as a sort of sanity check, you can get an overview of the messages that belong to a given capture. So shown here is one of those, and you can see here that interspersed with our normal application traffic against the staging server here with some collections there are all these ping commands. And this was a surprise to us. We weren't expecting to see this. At this time, we weren't aware of anything in our stack that would be causing these ping commands. We understood that this wasn't part of the Mongo driver spec, and we just didn't know that the Ruby driver was doing this. So we looked at it and puzzled over it for a minute, and we realized that it was this pinging that was ultimately responsible for this mysterious performance graph that came up earlier, where our monitoring tools were actually recording the time taken to do these pings erroneously as happening in Ruby time. So this graph that was behind this ghost that was haunting us the entire time actually turned out to be somewhat of a red herring and caused us to misunderstand and be really confused about certain things about our application. So sort of another example of how this process of building tools to understand what was happening in our application just led us to be able to work more efficiently and understand what was going on. So finally, this did end up being what we had known as the ghost the entire time, and when we did finally apply the patch that stopped these pings from happening unnecessarily, you can see in the corresponding graph here, this commands line previously was the sum of all activity. That's because we were firing a ping one for every other type of Mongo operation we were doing, and then you can see once we applied the patch, the number of those pings basically dropped off to the end. So yeah, as I said, this is a new thing for us. We're just starting to apply it and looking forward to the insights that it's going to give us to improve things. So that's Mongo Replay Capture.
Am I mic'd? Cool. Yeah, so we have a couple quick takeaways. And first is that knowledge is power. You can kind of see as you go through this how as we built more advanced tools and we built better visibility into what we're doing, we're able to solve these problems really rapidly. And being willing to be proactive is what can allow you to have that knowledge before something happens, like what happened to us last year, where we just weren't ready for something, we didn't have the tools, and effectively we got burnt. But once we have those tools, and now that we're being proactive with things like Mongo Replay Canon, we're prepared for these type of events in the future. The final lesson is that on any given day, for any given team, there's a different perfect solution. And throughout this process, we found a lot of strange perfect solutions. But if you look at perfect as being, instead of the traditional definition of perfect, but perfect being a solution that lets you survive and continue on to the next day, a lot of times this can be what you least expect. And getting through a period like we did last year took some creative solutions. So in closing, I do the hiring slide. We are very much looking for all of you. We're expanding rapidly. You can email us, mongodb@coinbase.com, or visit our career page. Very interested, obviously. And finally, before we get to Q&A, we have an event on Thursday. If anyone's interested, it is a Women at Coinbase cocktail hour. So if you are interested, women and allies, there's details here, but if you want to Google it, just Google Women at Coinbase New York City Happy Hour, and I'm sure you find it. So that's it, and I guess questions now.
Thank you very much, Luke, Michael, Jordan. Are there any questions from the audience? By show of hands.
Hi. Were you doing transactions with MongoDB prior to the transaction support or not?
No, we were not. We had built our own locking system to sort of get around the lack of transactions, and we're very excited about transactions that are coming. Yep.
So between sharding and memcache and the other twinnings which you have done, which was most fruitful to you? Like, compared to memcache and sharding, like which one do you prefer now? Now you have all the details about all your transactions.
I think the sharding thing is more natively supported and probably something that we should have tackled earlier and would have given us more headroom, I guess. Memcache was a band-aid, which has actually served us really well, and so it's still in production. But as Luke said, that any given day there's another perfect solution, and that just seemed to be the thing that worked for us that day. Yep.
Any other questions?
Hi. When you guys acquired GDAX, did you have to integrate any of their stuff into your MongoDB? What platform were they using?
So yeah, GDAX is a home-built product, but GDAX does not use for specifically their transactions. They use Postgres. However, they interact heavily with the Coinbase APIs, so inherently they're utilizing MongoDB there.
Okay, anyone else? Okay, in the back.
Good presentation, guys. Thanks. You talked about the pre-caching or caching the data in memory or memcache. So have you set up a TTL, or like you talked about invalidating when the data updates happens? Can you like give a line on like how you invalidate it, or is it out of the box?
Yeah. So we set a TTL on the cache key depending on how sensitive the data was, and then we would manually perform a memcache.delete whenever there was a write occurring. So there was sort of like a two-stage invalidation.
Okay, last question. Anyone?
As part of scaling, a lot of companies I see start breaking out their services into internal APIs, and sometimes they expose them externally as a developer platform. I'm curious, is this something that you guys are doing or considering doing?
Yeah, I mean, yeah, we're absolutely interested in doing that. In terms of how are we splitting things out internally, yeah, I mean, we'd like to break out a lot of logic. You know, we heavily utilize a monolithic Rails application. So yeah, there's certain logic that we are actively pulling out of that. Monolithic applications have their benefits as well, but in terms of kind of exposing that to, is that what you're asking, like publicly, like those APIs? Yeah, that's something we'd be very interested in doing in the future and are actively working towards.
Great. Thank you very much. This has been Luke Dumais, Michael DeHoog, and Jordan Sitka. Thank you very much for coming out. Please give them a hand.